Yeah, so to get to the point where you can analyze a dipole, you have to have already accomplished all the other steps in drawing Lewis structures and analyzing Lewis structure. You have to be able to draw a reasonable Lewis structure that's relatively stable. You have to be able to analyze the locations of the formal charges, which can be affected by resonance, so you've got to be able to look for resonance. You've got to be able to then redraw the molecule with a reasonable geometry so that you can see where all the charges are distributed. And then, once you've done all that, that's mostly the hard part. Then you just look to see where the charges are that you've drawn. If they're in the right locations, you just try to see if there's more negative on one side or the other, more positive on one side or the other, and then see if there's one side that's more negative, one side that's more positive, then you know that there's a dipole. So maybe we'll talk about an example here. C2O2H2. So I got to start by drawing my skeleton. I want my carbons in the center. And I'm going to put my hydrogens in last since they can only have one bond. And so in this case, I could put both oxygens on one carbon, or I could put one on each. I don't necessarily know which is correct. So I've got to kind of look at both options to see which gives me a more stable structure. Then when I put my hydrogens in, there's lots of options here too. Probably you would want to start by thinking about putting the hydrogens on the carbon, right? Since the carbon has a lower electronegativity, it should be our central atom. It should be the one that's more willing to share. So we put it in a position where it's sharing more. There are other options here. So if these don't work out, I've got to adjust the skeleton. And what I mean when I say not working out is that they've got to make noble gas configurations and minimal formal charges if possible. And if they're not, I need to consider other options and make the best option with the least amount of formal charge and complete noble gas configuration. So then I would count the valence electrons. I've got 2 carbons, so each carbon brings in 4 because it's in 4A, 2 oxygens, oxygens in 6A, and 2 hydrogens, hydrogens in 1A. So that makes 12 and 8, 22. 22 electrons. Both of my skeletons have 1, 2, 3, 4, 5 bonds. So 5 times 2 is 10. So I've already used 10. I've got 12 electrons left. And the guidelines say to put those electrons around the more electronegative atom first. So I'd put them here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do I have enough to complete all the noble gas configurations? That's the question I should be asking. I don't just put the electrons in and assume it's stable. What's missing? Well, in both molecules, I've got a carbon or more than one carbon that doesn't have enough electrons to make 8. So if my carbon that needs more electrons is directly bonded to an atom that has lone pairs, I just shift the lone pairs in and share them. And so I can do that here. I could shift these 2 in and share with that carbon. That helps that carbon. But I still have a carbon here without 8 and a carbon here without 8. So neither of those structures is reasonable yet. And if I find the atom that doesn't have enough electrons is not directly bonded to one that can share, well, this one is. So I could share here. And actually, I can actually share more here. I can make a triple bond, so that's not bad. That actually fixes all the noble gas configurations. That's not bad, so that's decent. The one on the left, though, this one here, it's not okay. Because the carbon there I highlighted in red needs more electrons, and the atoms directly attached to it don't have any to share with it, so it can't get more that way. So in order for that carbon to get more, I need to change my skeleton. I would need, if I were working on this one, I would need to swap the hydrogen with one of these oxygens. If I swap those, I still have the same number of electrons, all the same atoms. I'm just moving their positions. The reason I'm doing that is to position this oxygen next to the carbon so that it can share and satisfy the noble gas configuration of the carbon. So now I've got 2 options. that have all noble gas configurations. That's my priority when I'm drawing the Lewis structure. If you draw a Lewis structure and you've got a bunch of atoms that don't have noble gas configurations, then that's a really big problem, because you're not going to be able to do the rest of the analysis and you're going to miss almost all the points on that question. So start with that. Then analyze formal charge, because if you've got a lot of unnecessary formal charge, it's not the ideal structure. If you create a structure on your exam that has formal charges, but there was an alternative structure you could have drawn without formal charges, you're not going to get the full credit for that. So if I analyze the formal charge for, I'll call this oxygen 1, it's going to be oxygens in group 6A, so 6 minus the number assigned, which is the 6 lone pair electrons plus half of the 2 shared with the carbon. That's going to be 6 minus 7. That's a negative 1. So this oxygen 1 is going to be negative. That's not great. Again, the overall charge that's shown is 0. So all my formal charges have to add up to 0. If they don't, then the structure is completely wrong. I haven't even put the right number of electrons or atoms in, if that's the case. So not only do my formal charges have to add to the overall charge in the molecule, I also want to make sure they're as small as possible, or minimal. If I calculate the formal charge on this oxygen, I'll call this oxygen 2. It's going to be 6 minus, this one only has 2 lone pair electrons and 6 shared, so half of the 6 shared. That's 6 minus 5, that's plus 1. So this one takes on a positive formal charge. So that's not ideal. Maybe it's the best I can do, but I have to consider alternatives that don't create formal charge where I can. And that's why the structure on the left is a better structure. So this is the correct Lewis structure, because if I analyze the formal charges there are no formal charges. Each oxygen is 6 minus 6. The carbons are 4 minus 4. The hydrogens are 1 minus 1. So that would allow me to reject this structure here. I know that it's not as stable as it could be. It's not going to be the way that the electrons arrange themselves. So now I've got my structure. I've got the formal charges analyzed. I've got complete noble gas configurations. Then I want to look for resonance, because the resonance can affect where the charges are located if there were charges. Is there resonance here? What we said about resonance was it involves shifting the positions of the electrons without making the molecule less stable, because resonance is stabilizing. It will only occur if it makes the molecule more stable or equally stable. And the electrons that are capable of shifting will not move where the atoms, nuclei, are located. Only electrons are moving in resonance. And so the only way that can occur is if I move double bond electrons or lone pair electrons. So in resonance, I'm not going to be breaking single bonds. That's not resonance. I'm not moving those electrons to somewhere else in the molecule. The atoms are staying put. I'm just moving electrons in double bonds or lone pairs. So if I focus in on the lone pairs, then I could think about, maybe I'll take this lone pair and move it somewhere else. I'll move it in here. That's not good, right? Because it makes too many electrons on the carbon. So I cannot do that. That's not reasonable. It's not going to be happening. The other option would be to take some electrons from the double bond and move them out onto the oxygen. That's okay for the oxygen, but it's not okay for the carbon. So since it breaks the octet for the carbon unnecessarily and creates unnecessary formal charges, it's not going to be happening. So there's no significant resonance here, because even though technically the electrons can shift, which is resonance, it's not significant because it makes the molecule much less stable. So I'd say there's no resonance here. Now, before I can analyze polarity, I've got to analyze the geometry. Because if I don't draw the molecule in the right shape, if I put an arrow on it, that arrow really is pretty meaningless. So the shape is going to depend on counting up of the electron domains and the lone pairs and looking at the electrons spreading out according to the Vesper theory. So which atoms' geometries do I need to analyze? The carbon, right? Only atoms that are bonded to at least 2 other atoms. And when I analyze the geometries, I analyze them one atom at a time. I'm not going to look at the whole geometry of the whole entire molecule. I'm looking at the geometry of an individual atom that has more than one other atom attached to it. So the carbon in red looking at that one first, it's got 1, 2, because the double bond counts as one domain, 3 electron domains. So with 3 domains and 0 lone pairs, there's no lone pairs on that atom, so we're not saying there's 0 lone pairs in the whole molecule, just 0 on that atom. We're analyzing an individual atom. That combines to mean trigonal planar. Looking at the other carbon, it's got the same thing. This other carbon's got 1 bond to a hydrogen, that's 1 domain, a double bond to an oxygen, 1 other domain, and then the carbon-carbon bond is a 3rd domain. So that also has 3 domains. So I would label both carbons as trigonal planar. So they're both trigonal planar. That means I need to draw the molecule with at least roughly showing the 3-dimensional shape of what a trigonal planar is. So if it's planar, it's flat, which is nice because I can show the shape on a flat piece of paper. And the angles are all even. They're all basically 120 degrees. And that's pretty much how I've drawn it, right? So if you draw your Lewis structure differently, if you had drawn it like this, that's the correct Lewis structure. It's just not drawn with the right shape. Okay, so once you analyze that these 2 carbons are trigonal planar, redraw it and make them look trigonal planar if it isn't already drawn that way. Because if I analyze the polarity of this, it's not going to be correct. That's not how the molecule actually looks. I'm not going to create all this space up here and push the electrons close together when they're repelling. They're not going to be pushed close together voluntarily. They're going to spread out. So since they spread out, the trigonal planar shape is created, and that's what my molecule looks like. Now, to analyze the polarity, which was the whole point of doing all this, I need to analyze where all my charges are located and see, are they evenly distributed or not? So I can use this vector method, and using the vector method, I'm going to analyze each individual bond and see whether the bond, what direction the bond points in, what side's negative, what side's positive. So I would need to know that carbon's electronegativity is 2.5, oxygen's 3.5, hydrogen's 2.1. So now, if the atoms are sharing electrons and the one atom's more electronegative, that creates an arrow toward the more electronegative atom. Oxygen's more electronegative than carbon. Carbon's more electronegative than hydrogen, and oxygen's more electronegative than carbon. The arrows I use in my vector method, though, have to represent not just the direction, but how much of an electronegativity difference there is between the atoms. So because carbon and oxygen have a large electronegativity difference, and carbon and hydrogen have a smaller electronegativity difference, the carbon-oxygen arrows will be longer arrows. So then I'll just maybe label these so you keep track of which arrow belongs to which. You don't necessarily have to do this, but arrow 1 is the CO double bond. That's going to be a long arrow pointing up and to the right. Arrow 2 is pointing down and to the right, but it's a shorter arrow because of the carbon-hydrogen electronegativity difference being a smaller difference. Arrow 3 is another very long CO, same distance as the other CO because it's the same electronegativity difference. And then arrow 4 is pointing up and to the left. And so I get right back to where I started. So that means this is nonpolar. The other way to analyze that is to draw in where all the charges are. So if the CO double bond shifts electrons toward the oxygen because it's more electronegative, I'll create a significant partial negative on that oxygen. That happens on both oxygens. And a partial positive on the carbon as a result. Then the CH bond is very slightly polar, so that will create a slight partial positive on the hydrogens, not much. So where's the average location of negative? It's between the 2 sites of negative. The average location of positive is between all these partial positives. So because of the symmetry, the average position of positive is, in between these positives, right in the middle. And the average position of negatives in between the negatives, right in the middle. And so when the average position of positive and negative are in the same location, that's what it means to be nonpolar. So both analyses give me the same answer, that molecule is nonpolar. Now if you had shown the molecule a little differently, and this illustrates something that you'd see in a couple of the lab examples as well. Oops, I drew it the same way, not differently. If I had happened to connect the oxygens both pointing up, is there any difference in stability between that and the original one? No, they both have complete noble gas configurations. There's no formal charge. Everything's stable. Now if I analyze the polarity, though, by either method, I would have found an arrow pointing straight up, because all of the negative is at the top on the oxygens and all the positive is at the bottom between the hydrogens and the carbons.
I just had a question. Would this would that also be possible?
Let's take a look at that. So he made a, was it like this?
Yeah. And there's a double bond with the oxygen.
Oh. So that's okay in that all the noble gas configurations are good. But then you've got to analyze it for formal charge as well. So if you do it this way, you're going to end up with a negative on each carbon and a positive on each oxygen. And that's not ideal. So if that happens, you could think about shifting the electrons around. So we could think about putting the double bond between the carbons and the lone pairs on the oxygens. So if I redrew that and put the double bond here and then connected the oxygens and gave the lone pairs there, then I don't have any formal charge. So that's definitely way better that way without any formal charge, much more stable. There are a couple of problems with this though, and I talked about this with some of the lab groups, and that is if you try to bond two electronegative atoms together, because they're both pulling on the electrons, the electrons aren't really stabilized well by either atom, because they can't really get as close to either nucleus as they could if they were arranged in a way where the electrons are shared between elements with different electronegativities. So that's not ideal. It's not impossible. It's not ideal. And if you try to connect a ring like this, where everything's connected in a circle like that, because the geometry is limited by the geometry of a square, since I've got 4 sides to it, that creates an angle here that's 90 degrees. And so what should the geometry of those carbons be based on the number of electron domains they have? It should be trigonal planar, so the angle should be 120. So that means if you connect it in a square like that, you're distorting the angle from its optimal angle of 120, which is optimal because the electrons repel and they want to spread out. You're forcing them into an angle of 90 degrees, which is also not as stable. So it's not ideal, and which is why we haven't been drawing molecules in a ring like that. It turns out if you have usually 5 atoms in the ring, or 6, then you don't have such tight angles, so that's much more stable. So that happens a lot, and there's one example on the lab, the C6H6, where the most stable structure you draw would have a 6-membered ring between the carbons. That doesn't create, if you draw a hexagon, a 6-membered ring, the angles are all 120. So with those trigonal planar carbons, they don't have to distort their angles at all. That's perfect. So there are, there's some other subtle things that can affect the stability beyond just the noble gas configuration and the formal charge, but we're not trying to get into too much detail. We want to focus on those 2 major factors as well. So if you had drawn this structure, with complete noble gas configurations and no formal charge, I might only take off half a point or something because it's not quite as stable as it could be. But you've done pretty much your job. And if you were to analyze, the geometry and say that the carbons should be trigonal planar and that the oxygen should be bent, even though their angles are not ideal, at least you've labeled the geometries correctly. And if you were to show that since the oxygen is more electronegative, again, the polarity is shifting toward the negative side of the molecule, and you correctly identify the direction that that molecule would have in terms of its dipole, that would be great. So you get, like 5.5 out of 6 points or something like that. So that would be fine. Yes. Sorry.
No, okay. All right. So when you did the general direction of the whole molecule polarity, you had pointing straight up, correct?
Yeah, I did.
Then maybe I'm missing something about that because I'm not sure why it's doing it when you never wrote it down wrong, but I thought it was going a different way.
So if I were to analyze this one, looking at the vector method, I would recognize that the oxygen's pulling electrons, so those are pulling electrons up. The carbon's more electronegative than the hydrogen, so those are pulling electrons up. So if I number these, 1, 2, 3, 4, if I start with arrow 1, that's a tall arrow pointing up to the right. I'm gonna need more space here.
I get what you're saying now.
Uh-huh.
Because on the last model, you had a switch for carbon and oxygen down
Right.
there, so that's why it would point this way as well as up this way.
Right.
But it doesn't
Right.
make sense having both that way. It has to go one direction. So in essence, that last model was not really the true way you would
No,
find
so
it.
what I was saying was, yeah, that's a good point. So what I was saying was, this is perfectly stable, but it happens to be polar. The other alternative, where the oxygens are pointing in opposite directions, is also perfectly stable because it has noble gas configurations and no formal charge. It just happens to be nonpolar.
Yeah.
So what this means is that because the carbons are connected through a single bond, the single bond can actually rotate. So this will be like a propeller, and those oxygens, sometimes they'll be on opposite sides, sometimes they'll rotate to the same side. So the same molecule, depending on how it happens to rotate at that moment in time, it might become polar when initially it was nonpolar, or vice versa.
So to be safe on that, if it has the ability to rotate like that, we would write both models representing one being polar and one not being polar?
Correct. On the lab, that's what I would expect you to do. For the exam, I'm not going to expect you to go to quite that level of deep. For the exam, it would just depend on which one you drew. If you drew this one and you showed polar, I would give you full credit. If you drew this one and showed nonpolar, I'd give you full credit. If you drew both and said it would depend on how it rotates, also full credit. That would be okay for the exam. Right. For the lab, though, there are a couple in the lab that have that type of situation where the bond can rotate. If the bond can rotate and it goes from polar to nonpolar, you should recognize that on the lab and be able to describe how the molecule will go from one polar to a nonpolar state depending on how it rotates. And be able to draw both of those types of rotations. Other questions? Yeah.
Just on the YouTube Lorain chapter, it talks about why atoms are more electronegative than others. Is that, I guess, can you just...
Sure. So the electronegativities for any of the atoms that you have to draw molecules will be on the exam. So you don't have to memorize the numbers. But I might ask you to explain why different elements have different electronegativities. So we talked about on the periodic table,
higher in the right corner?
the electronegativity goes up as you go to the right and as you go to the top. And so that's the same reason that the electron affinity goes up in the same trend and that the ionization energy goes up with the same trend. And that is because elements at the top have less shielding. And as you go across in a given row, you're putting in more protons. So with more positive charge, as you go to the right, you increase in ability to attract electrons. If you're talking about electronegativity, you're attracting electrons from a shared pair that atom's sharing with another pair. So more protons will pull them away from the other atom that they're sharing with. And less shielding will also attract them closer to the nucleus.